Hello and welcome to this session on generative models, a critical component in the Retrieval-Augmented Generation (RAG) framework. In today's talk, we'll explore the evolution of generative models, focusing on transformers and large language models (LLMs). By the end of this session, you'll understand how these models generate text, why they are so effective, and how they fit into the broader landscape of AI and data science. Let's begin. What are generative models? Generative models are algorithms that generate new data samples that resemble the data they were trained on. In the context of natural language processing, NLP, these models produce text by predicting the next word in a sequence, allowing them to craft coherent and contextually relevant responses. At their core, generative models learn patterns from large data sets and use this learned knowledge to create outputs that are statistically similar to the original data. This process powers applications such as text completion, translation, summarization, and content generation. The rise of transformers. Transformers have been a game changer in the development of generative models. Introduced by Vaswani et al. In 2017, transformers replaced recurrent neural networks, RNNs, and long short-term memory networks, LSTMs, as the dominant architecture for NLP tasks. What makes transformers unique is their attention mechanism. Unlike previous models, transformers can analyze entire sequences of text simultaneously rather than processing data sequentially. This parallelization significantly accelerates training and enhances performance, allowing transformers to handle large-scale datasets efficiently. The transformer architecture forms the backbone of most state-of-the-art generative models, such as GPT, Generative Pre-trained Transformer, and BERT, bidirectional encoder representations from transformers. These models have achieved remarkable success by learning contextual relationships within text, making them adept at generating human-like language. Large language models, LLMs. Large language models, or LLMs, are an extension of the transformer architecture. These models are trained on massive corpora of text data, often involving billions or even trillions of parameters. Examples include OpenAI's GPT-3 and GPT-4, Google's Palm, and Meta's Llama. LLMs work by generating text one token at a time, predicting the most likely next word based on the context provided by the preceding words. This allows them to produce long, coherent passages of text across a wide range of topics. One key feature of LLMs is their ability to perform tasks with minimal supervision, known as zero-shot or few-shot learning. By simply providing a few examples or a well-crafted prompt, LLMs can adapt to new tasks without the need for extensive retraining. Advantages of transformers and LLMs. Transformers and LLMs offer several advantages over traditional models. Scalability. Transformers scale efficiently, enabling the creation of models with billions of parameters. Contextual understanding. The attention mechanism allows models to capture long-range dependencies and contextual relationships within text. Versatility. LLMs excel at a wide variety of NLP tasks, from language translation to code generation. Minimal fine-tuning. LLMs can perform new tasks with minimal retraining, making them highly adaptable to different domains. Challenges and limitations. Despite their success, transformers and LLMs are not without challenges. Resource-intensive. Training large models requires significant computational resources and data. Hallucination. LLMs can generate plausible but incorrect or misleading information. Static knowledge. Once trained, traditional LLMs lack the ability to access new information unless retrained, which limits their relevance over time. These limitations have driven the development of Retrieval-Augmented Generation, or RAG. By integrating retrieval mechanisms with LLMs, RAG ensures that generative models can access external knowledge, reducing hallucination and enhancing factual accuracy. How generative models fit into RAG. In the RAG architecture, generative models work alongside retrieval systems. The retrieval component pulls relevant documents or data, which are then fed into the generative model to produce grounded, accurate text. This symbiotic relationship allows it to leverage the fluency of LLMs while anchoring responses in real-world knowledge. For example, if a RAG model is asked about recent scientific breakthroughs, the retrieval component fetches the latest research papers. The generative model then synthesizes this information into a coherent and comprehensive response. Real-world applications of generative models. Generative models power a wide array of real-world applications. Chatbots and virtual assistants, providing human-like interactions in customer service and support. Content creation, assisting in drafting articles, blog posts, and marketing copy. Medical and legal, summarizing complex documents and research papers. Coding, tools like GitHub Copilot use generative models to assist developers by auto-generating code snippets. In summary, transformers and large language models are at the heart of modern AI advancements. Their scalability, versatility, and contextual understanding make them essential for building cutting-edge generative applications. When combined with retrieval systems in RAG, they address key limitations, paving the way for more accurate, dynamic, and reliable AI systems. Thank you for joining this session. In our next module, we'll explore how retrieval and generation interact to create powerful hybrid AI models. I look forward to seeing you there.